I'm Nicolai Parlog. I'm a Java developer advocate with Oracle, and I'm here to tell you about Amber, Loom, Panama, and Valhalla. So there's a lot to go through. The slides are online. You can go to slides.nipafx.dev, and you will find them there, and you can follow along if you want. Brian Getz, who's working on Project Valhalla, has once been told that he's working on like 6 PhD theses in one project, which by some quick math tells us that we are going through 24 PhD theses in 50 minutes is what the screen tells me. So that means we're in a hurry. Just in case we don't get to questions, which is very likely, I'll be around the conference today and tomorrow. I got to leave on Friday. But yeah, so you can always flag me down. I got a green button here, so that means you're totally allowed to talk to me. I would actually appreciate that if you have any questions. And yeah, I think with that, we can get started. Oh yeah, right, the other thing. This is no tutorial. I'm not teaching you how these individual features work because A, they're not final yet, and B, we wouldn't have the time anyway. So this is more to get an impression of how these things operate and take that home with you and then look forward to when they actually get finalized over the next coming years. So let's start with Project Amber. There's lots of links here to the project, to the wiki, to the mailing list where you can follow along how the project is evolving. Launched in March 2017 and is led by Brian Getz. And the basic goal is, or the motivation behind Project Amber, is to tackle some of these shortcomings that Java seems to have, that in some cases it can be cumbersome to use, require a bit of boilerplate, and overall there are some situations where you just cannot clearly express the thing you want to express. Like you have to write all the boilerplate to, transport what you actually want to say. And the idea behind Amber is that it continuously improves that situation. So Project Amber is not a solution to a problem, as a solution factory to a larger problem, right? So it's probably not going to end anytime soon, just going to keep looking for places where it can, in small and meaningful ways, improve the language. And already did that over the last couple of years. It gave us switch expressions in Java 14, all the way up to seal types in JDK 17, also local variable type inference, not to forget that, in JDK 10. So there's already a bunch of stuff that it delivered, and we can sort those a bit, and we see that seal types, records, type pattern matching, and switch expressions. Those 4 are somewhat independent language changes. Actually, they're mostly independent language changes, but they come together really, really well in this concept of pattern matching. And the cool thing about pattern matching is that it's a very light topic people love to talk about. So there's a presentation, I think, in just like 3 hours and a bit by Peter Wessels and Hanno Embrecht. That's complicated. So by Peter and Hanno. And so if you want to know more about pattern matching, go to their talk. I'm sure they're going to do a good job explaining what all that is all about. And that frees me up to talk about something else. So let's talk about something else that is brewing in Project Amber at the moment that is not, I think there's a JEP draft for that. So it's still very, very early, but it's already something that we can just take a look at for fun. Maybe it ends up like that in the language. That would be cool too. Okay, so let's talk about string composition. So we're trying to put strings together. Laser pointer really doesn't work on a screen, huh? So we're trying to put strings together. We have a property and a name, and we want to create a simple SQL query that says, give me all the people. And so we have to put the property and the value into that string somehow. We could use just the plus. We can use formatting. There are a few more options, but they all amount to this. And not only are they cumbersome, they also come with a free SQL injection. Wouldn't this be cool? This is what other languages offer. Like not exactly like this, like how exactly is the property or the reference to the value, how are these exactly coded? That differs from language to language, of course, but it could be something like this, which would be much simpler to create an SQL injection. But it would still be more elegant, so there's that. And SQL injections are not the only concern here. Obviously, there are other formats. Actually, most formats that we ever want to create where we want to put values inside a string, most of those are not natural text. They're meant to mean something to some system. HTML, JSON, YAML, all of those have format-specific validation, verification rules, and all that needs to be something that if we want to use a really good way to put together strings, we should be aware of. And so this is where string templating wants to come in. As I mentioned earlier, there's a JEP draft. A JEP is a JDK enhancement proposal, which is basically an architecture decision record, I think is the nominal term for that, which says this is the problem we want to solve. These are the goals, the non-goals, the proposal, alternatives, and they're great. Like they're great technical documents to read. They're not hard to understand. Like if you're decently experienced Java developers, you will, just breeze through most of those. Some technical parts are a little more involved, but mostly they're really good to understand. I can only recommend reading them. So they go through a draft state, and then at some point the JEP is finalized, and then maybe it changes a bit, and then the feature shows up. So all this process takes time. This feature is very early in that process. And the idea here is, and I use the text blocks here, is that you have this text block thing, right? So it says select star from person where, and it uses this new syntax to embed the values there. And this is what's called the templated string. The interesting thing is that there's also an str dot before that. And that's a template policy. So the proposal is to have 2 steps and not just 1 step. The first step is have this templated string, write that out in the language, and then have some policy that transforms that into an actual string. So for example, we could do this, right? So we have a description here, we have a price, a quantity. Those are all variables that we have lying around somewhere. And the idea is to put all those together into the string to give you something like a receipt. And that, would work. This str policy really just concatenates strings. It does nothing fancy. And you end up with stuff like this, which is not how we usually write down text or monetary amounts with 3 decimal positions. So there could be another policy called formatter, I think. That's what it's called. And this one could understand the formatting substrings, right? So this one you could say, okay, maybe I just want to have always like a leading space if it's just 1 digit, and I want to have 2 digits behind the decimal point. And then this policy could, do all of that. Pretty cool. But then the JEP does the really cool thing that I found very impressive. It takes a step back and asks, why are we just talking about strings? So we just discussed how we can put information together into a string, which is great for the examples that I showed you. But very, very often, like with the example about the SQL query, we don't actually want to use the thing that we create as a string. We just use the string as an intermediate representation on the way to something else. So we start with the string and values, then we validate and sanitize, hopefully, because that's something the policies can do. And then we end up with a string, and then we give that string to some other subsystem which then invests a lot of time and energy to parse all of that. Why the detour? Can we skip that? And the proposal is, yes, let's skip that, if necessary, or if reasonable. Because the template policy is an interface that takes a templated string and gives back not necessarily a string. It can give you back whatever kind of type. And that's pretty cool, because that means we could have a templating policy that's called SQL. I made this one up, so that's not even mentioned in the JEP, in the JEP, I think. So you could have like a templating policy like this, either in the JDK or contributed by libraries and frameworks. So this would not just be available for the language. We could create our own template policies. And this would then do, you know what, we're just going to do the sanitation. We're going to make sure that there's no SQL injection. But we're also immediately going to return a statement. Because you don't want a string, really. What you want is a statement. And the same thing with JSON. If we put some JSON together, maybe we want to have it as a string to feed it into a test. But maybe we already want to have the JSON object, just to be immediately able to then work on the JSON document that we created there. And so the custom templating mechanism will allow us to start with a string and some embedded values and end up with an actual object that is more involved than just a plain string. Once again, I find pretty cool. So overall, as I said, template strings are in the early stage, and there are other endeavors going on. And I'll link to a bunch of sources here. So I think what's going to happen next is just finish pattern matching. There's probably, oh yeah, it was a JEP draft, right? I think now it's actually a final JEP. I think I didn't update this. I think it's 427 at this point, this one. Then we're probably going to have more patterns. There's already JEPs for that. And then there are 2 other features that are even further down the road. Maybe we get concise method bodies. I'm not going to go into detail what that means. And maybe we even see a new and less invasive way to handle serialization. All of that would fall under Project Amber. So it makes Java more expressive. It wants to reduce the amount of code that we write. Records are like a prime example of that. And also wants to make us more productive, right? By allowing us to more clearly express what we want to the language, but also to our colleagues. Now at this point, usually people ask, so when is all of this going to happen? And when I ask my colleagues, when is this going to happen? They're going to give me a very official answer. When it's done, it takes time, blah, 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 which makes sense. And really, anything else we could do is speculation. which is fun, so let's do that. So this is my personal speculation. Yes, I work for Oracle. No, you cannot sue me. I'm not very rich, so I'm like, don't bank any money on this, right? These are just personal guesses. And that is that hopefully next year patterns in Switch will be finalized. I hope that we see the first previews for deconstruction patterns and for template strings. Maybe I was hoping for 19 a bit, but it doesn't look like it's going to make it. I'm not sure. So, all right, I didn't finish that part. I didn't ask my colleagues. So instead, I based this on publicly available information, the mailing list, the JABs that you read, and you get a little bit of a feel for how long stuff takes. So that's why I would call them educated guesses. And then I'm pretty sure that once we got the basics of pattern matching down, we will see more patterns in the future. There's a bunch of thoughts already on that. Okay, there's more links if you want to learn more about pattern matching specifically, but about the Java language evolution by Project Amber in general. I highly recommend looking at those documents or the videos. And with all of that said, let's go to Project Panama. So, Project Panama is about interconnecting JVM in native code. Once again, all the links, and it already ran for quite a while. At the moment, it's led by Maurizio Cimadamora, and it has 3 sub-projects. Of which the second 2, so the last 2, foreign memory and foreign function API are strongly connected, whereas vector API is totally off to the side. I want to talk a little bit about that. So let's talk about a concept called vectorization. So let's say this is what you want to do. You get 2 arrays, A and B, and you get that's input, and as an output, you have the result array C. And what you want to do is pretty simple. You want to square A, add the square of B, and then take the negative of that number. And you want to do that for all the numbers in A and B. And we assume they're all of the same length, so this makes sense. So this is what you would do, right? You write a loop that goes from 0 to the length and then does the computation. Easy enough. Now it turns out that your CPU can actually do much better. While we think of these operations one by one, the CPU has so-called multi-word registers. They can go up to 512-bit on this laptop. It's 256, I think, on my Ryzen at home. And that means you can store a bunch of numbers. So for example, if you do have 512 bits, you can store 16 floats in one of these registers. So instead of adding one float, 132-bit float, and another one to one result, you can have 16, and then another 16, and then compute them to 16 results. This is not parallelization. You're not using different CPU kernels or CPU cores. You're just using one CPU core. It just does these in essentially the same time that it would take for simple computation. This is called single instruction multiple data, because the instruction is add, and the multiple data is 16 pairs for which you want to produce 16 results. And the just-in-time compiler knows about this. Many CPUs can do this, and the just-in-time compiler tries to aim for that. It really tries to figure out, okay, is this a situation where I can unroll the loop and then figure out that this is a block of the same operations? Then I can use this for the underlying, and it works somewhat, but it's not super reliable. Like, it's a great performance boost that you get for free, but you can't rely on that being there. And this is where the vector API comes in. We're not going to go like over the details of all of this, right? So the first thing I want to talk about is the vector species at the top. That's basically capturing what on my system, on that one, would be how many floats can I fit in one of these multi-word registers, which on a different system would be a different answer. But that's abstracted away. And then what I do is I go over this loop in the length of this vector. So if I can pull 16 floats into there, I go in 16 steps, in steps of length 16 over that array. And then I pull from the array the vector A and vector B, and then I do computation at the bottom, and then I write that into the result array. And this can yield a speed up of up to, if it's 16 floats, of x16, which is pretty cool if you're doing this kind of numerically intensive operations like image manipulation or Mandelbrot computation is something that Intel uses as a demo for this. So a bunch of, like, it's not something that we do super often, but there are specific places where this makes a lot of sense and where this API will do a lot of make a big difference. It's a comparatively clear and concise API given the complex requirements. It's platform agnostic, so you can always use this. Even if the target system doesn't actually have that, that's the last point, graceful degradation, the just-in-time compiler will always turn this into the optimal code for your machine. And if that optimal code is a regular loop, you will get the regular loop without any perceivable performance disadvantage. So you can never get worse, but you can get much better on basically every modern CPU. Okay, that was vector API. Now let's quickly touch on the other 2 topics. On foreign memory and foreign function, just want to have a few words on that. So these are like 2 somewhat different problems. The first one deals with how do I store stuff off heap? If I, for some reason or another, I want to manage memory on my own, I can put stuff off heap. The public API for that is a byte buffer, but that is limited in size and it's also somewhat inefficient. And the fast way to do it is unsafe, which is unsafe and not recommended to use, so that's not ideal either. So there's like a tension between, do I want to do the right thing or do I want to do the fast thing? And JNI, which is the Java native interface, which you would use if you call, for example, into a C library, that's not ideal either. So it involves several like tedious artifacts and tool chains to get everything working together. It's not super interoperable, and like the type systems that are different between Java and C are not reconciled. And these are problems, they go somewhat together, because if you want to call into a foreign, into a native library, and you want to get some results back, or you want it to work on a larger data structure, you need to put your JVM managed information off the heap, so that then the native code can operate on it, and then you need to get it back. So that's the connection between the two. And so this is where these two APIs come in. The foreign memory APIs is a safe and performant way to deal with off-heap memory. And it has a bunch more classes than just byte buffer, memory segment, memory address. And the really cool thing is that at the bottom, the control DA location, because the problem with the byte buffer is you reserve 2 GB of off-heap memory, you don't need it anymore, you kind of want to get that memory back. But the garbage collector only sees a byte buffer instance, which is really small because it's basically just a pointer into memory. So it doesn't have, it's not in a big rush to clean up that byte buffer. And if it doesn't, the 2 GB keep blocked. That's not great. So the memory session gives you different ways to scope this. To say within this method, I want to, like when the method is done, you can release memory, or when only this thread can see that, then that doesn't have to be thread safety, which makes it faster. So that's a very important part to allocate how the memory is used and when it gets deallocated. That makes it easier to put stuff off heap for a variety of reasons. One of them could be to call into native code, which is where the foreign function API comes in, which is a streamlined tooling and API to call into native code. So it has a bunch of like low-level stuff, like the linker and the descriptor and the native symbol. And what that essentially does, it uses method handles to allow you to call into native code. And you can generate that with JExtract. So the idea is you take a C header file, you take a C file, you generate with JExtract these very low-levelly but still Java code classes, and then you put a proper Java API on top. And every time the C library changes, you just regenerate that file, and then the compiler will tell you, well, you're calling a method that isn't there anymore, or the number of arguments changed or whatever, so that most of your development you can do in Java, and only like the generation is where you have to interact a lot with the native code. And that's also something that's hopefully faster than JNI. Specifically, upcalls are slow in JNI. When the native code needs to call back up into the JVM, that's apparently very slow. And JExtract, foreign function API makes that faster. So this is not just my guesses, these are the official plans. The foreign memory and function API will preview in JDK 19. That's the JEP 424, which is already published. And then the vector API is basically pretty much done. Like it could be merged and be ready, but the problem is that it wants to wait for Valhalla because it will really improve with Valhalla, and it doesn't want to finalize the API now, and then in a year we'd be like, well, it would look much better now and would work better now. So it will probably stay as an incubating module until then, which is a bit unfortunate. But it's pretty stable too, so you could write code against it. There's some deeper dives here. The Gunnar Morling from Red Hat wrote a cool article which is called FizzBuzz SIMD style, where you use the vector API for FizzBuzz. And then on the foreign APIs, there are these state of the documents, which are really great to understand better what the design is and why it's that way. I only recommend taking a look at that. Okay, next one. Okay, we just did 6 times 2, so 12 PhD theses. I think is pretty good. We're good in time. Okay, so let's talk about Project Valhalla. It talks about advanced Java VM and language feature candidates, that's the really weird mission statement because it tells you nothing. At least it didn't tell me anything. But what it really is about is to overcome Java's split type system. Java's type system knows primitives and classes. Well, enums are classes, interfaces are classes. So by that vocabulary, like everything is a class, basically, which the JVM also agrees with. But you have that and primitives, right? And we can only create classes. We cannot create primitives. And the classes we create all have identity, and there are always references. And this is often useful, but not always, and it comes with downsides. So if an instance of a class has identity, that means if you write new integer 5 and another new integer 5, and you ask whether they're equal, then yes, they're equal, they're both 5. But if you ask whether they're identical, meaning that two equal signs, then they won't be, because a new integer 5 is a different instance from another new integer 5. So they will not be identical. And this concept of something that can be equal but not identical requires that you track where an object actually lives. That requires a memory header. That is necessary for mutability. And that also allows locking and synchronization. But not everybody needs that. We don't need all of that stuff every time for every class. And also references are not without trade-offs. So the reference is, if you have a Java object, it's basically just a pointer to where the actual information lives. And that memory access indirection can actually be a problem. If you want to write high-performance code and you want to have an array of two-dimensional points, what you're getting is an array of memory addresses, and every 2 dimensions you have to then jump all over memory to try to get all the stuff that you actually want to have in the array, which is x and y coordinates probably. It allows nullability, which could be seen as a good thing, but okay. But you need that, right? Like if you don't have a reference, you can't have null. Like you cannot have like a small, like a lowercase int. That cannot be null, because all zeros is 0 in int. So there's just no way to represent nullability without references. And we're not going to talk about tearing a whole lot, but references also protect from that. Again, not all types need that. And here's where Project Valhalla comes in and says, okay, we're going to allow you custom types that we are going to write that gives us the chance to say, I don't need identity, that would be value types. I also don't need references, that would be primitive types. And then universal and specialized generics want to mend that rift in the type system, where you can, with universal generics, you'll be able to use the existing primitives and all your own value types and primitive types in generics. So you can write an array list of int. But that only means that you can write that, and there will be bytecode that works with that. That doesn't yet mean what we really want, because that would still involve boxing, until specialized generics is implemented. Specialized generics will then be, okay, now let's really use the JVM commands that operate on these primitives. So you can then have the array list not of int, not backed by an object array of boxed integers, but instead actually have the just-in-time compiler generate code that uses an int array as backing for the array list of int. And of course, not just int, right? For all the primitive types and also for all the types that we create. So let's go to a little bit of an example with value types. Let's start there. I want to have a rational number that needs a nominator and a denominator. I would add constructors and everything. The critical part is the value at the beginning, right? It's value class rational number. And you can write, like this is basically just regular class. There's, you have a lot of freedom. There's some limitations. Classes and fields are implicitly final, which makes sense for values. And you cannot have any kind of superclass. But you can have super interfaces, you can add all interfaces generally. You can add all kinds of methods. Like this is like any other class, except for those two limitations. At this point, you say with value type, I don't want identity. So if somebody uses your type as if it had identity, for example, to lock on it, then the runtime would allow to throw an exception at that point, which is different from now. Right? At the moment, you can take any object and just synchronize that object. I don't think we should do that, but we can. And then the identity check, which is the double equals, compares by state. Right? It doesn't have an identity to compare, so it would instead compare the actual values that are contained by that type. And the big benefits of this are twofold. On the one hand, you get better expressiveness of the language. You can say, no, this is a value, which means something, for example, in domain-driven design. It's definitely immutable. And on the other side, what you get is the freedom for the JVM to do optimizations, because it doesn't have to track identity anymore. It can reduce the memory overhead, and it can generally be better, like it has more freedom in optimizing the code. So it's going to give you more performance. The value type behavior is still a reference, though. Sorry, the value type is still a reference, though. So null is a default value, and you don't have tearing. Once again, let's not go over that too much. The idea is that there are a bunch of so-called value-based classes at the moment. So this concept of value-based classes was introduced in JDK 8. Optional is one of them. The Java Time API, all of those are value-based classes. If you read the Java doc for optional, you will see that it says at the end, this is a value-based class with a link to a document, and that document tells you, also in the Java doc, what you can't do. You cannot synchronize. You shouldn't do an equals like the double equals sign comparison. That you shouldn't do an identity check. You should do nothing that relies on its identity. And the reason for that was the hope that this would work out, that the JDK, as well as other libraries, they have many value-based classes, and we plan to migrate, so we being, that's a language from the JEP, we plan to migrate many value-based classes in the JDK to value classes. So the JDK hopes to use this feature itself, of course, for all of these types that should actually be values that can now be expressed as values. The next one is primitive types. I have a complex number here that has a rational and an irrational part. And a primitive class is just like a value class with the exception that it cannot reference itself. You cannot have a field of type complex number. Put a pin in that, we come back to it in a second. But other than that, like, it's pretty much like a value class. But you don't have references. So like a value class, it doesn't have identity, but on top of it, it says, I also don't want references. And that means it can't have null. And that means it must have a reasonable default value. And this was a long conversation. Like Project Valhalla originally only wanted to introduce one kind of type. For example, let's say value classes or value types. That was the original plan. But this point about null was a serious contention. The problem with that is, if you don't allow null, then as I said, the default has all fields set to their defaults. And that makes sense for a rational number, right? So a rational number where rational and irrational is, sorry, a complex number where rational and irrational is 0, that makes sense. That's just 0. But earlier, the example that I gave was a number that has a nominator and a denominator. And a denominator of 0 doesn't make sense, because then it's an illegal number. Like, you start off the gate, the default value is an illegal number that falls apart under any kind of arithmetic. It's probably not helpful. So that was a point of contention. Like, how can we make sure that not everybody has to pay for references by not getting all the performance improvements? But if you throw out references and then disallow null, that could also be a problem. So that's why we have value types or value classes value types and primitive types. So the idea is that there are no references, so they can't have null. That means the default value has all fields set to their defaults, as I said, and once again, they can be tearing now. And the benefit for this is that the JVM has even more freedom to optimize code. It doesn't have to hand around, it can create a position in memory to store and just hand around a pointer if it wants to, if it thinks that's faster. But it can also do what it does with an int, namely just copy the variables onto the stack every time a method is called. So it gives it the freedom to make primitive types basically as performant as primitives are today, which is pretty impressive. So that means we can have our own stuff. We can have unsigned int and all of that stuff that we always wanted. We can create that without it being slower than the primitives that are built in. Okay, I said earlier, like, it can't have primitive type, can't have self-references. And I said to put a pin in that. We're now going to slowly start taking that pin out. So let's start with the example of int. Even int sometimes wants to be a reference, right? So sometimes we want to have a variable that is, yes, it's an int, but we want it to be nullable. We want it to be able to reference itself, not with an int, but with a node in a list, right, that knows the next node in the list. That's a reference to the same type. So what we do with int in that case is we box it to integer. So sometimes we want to box stuff. That's still something we occasionally want to do. So what can we do with complex number? And now this is pretty deep into the JEP. Like, if you don't get all the details and take all of those home, that's fine. I will have links to the JEP later. If you're interested, read up on it. I'm just going to give you, like the short version. It's fine not to, grok all the details immediately. The idea is that if I write a primitive class, like P, what I get are two types for that. I get P, which is, as we discussed so far, which is the primitive type, which has no references and no identity and all of that. But then there's a second type, it's called P.ref, and that behaves like a value type. That's basically the box. That's the box for integer. The box for int, which is integer. And that way I can have a primitive class node, which has some value here, and it knows the next node by containing a reference to the next node, right? So you cannot embed the next node. If you have a type and you want to put a value there and then a reference to the same type again, then how wide is that going to be in memory? Is it like just one more node, or does that node contain more nodes? That wouldn't work. You want to have a reference there. And that's why that's what you can use this for, and then go around the limitation of no references. And the goal here is, on the example of int and integer, we want to adjust the basic primitives to behave as consistently with the new primitives as possible. So the idea is that, conceptually speaking, instead of having a class integer and then a lot of special treatment for int, what should basically happen is we create a new primitive class called int. We give it all the code that used to be an integer. Now it's a primitive class that behaves just as performant as int did in the past. That's the promise, right? And then we say, okay, int.ref, the box for int. We're just going to alias that to integer. And then we can remove the class integer. So that means the integer, of course, like both int and integer will remain words that the JVM and the compiler understand. Otherwise, that would probably a bad thing considering backwards compatibility. But so the concept would be all the code goes into int, and integer basically just becomes an alias for the value type that is the wrapper, the box for that primitive type. And the interesting bit here is that means int gets methods. All these primitives have methods then. You can call like 5.toString. Not sure like how often that happens to you, but whenever I have an integer but I need it as a string, I'm like, okay, either I call like the official toString method, which is like integer.toString, and then I give it my integer, which sucks, or just have like empty string plus the int, which makes me cringe every time, but it's still like the shortest way to do it, and now I can just write 5.toString, so maybe that's acceptable too. But if I know the word, the 5, I can of course put it in the quotes, but you get it. Okay, so that was value types and primitive types. Let's talk about generics. That's pretty straightforward. Because when we all create these kinds of types, we don't want them to be like, we want them to be able to work with generics. It would be unacceptable for us to create value types and primitive types, and then every time we touch generics, the compiler says, nope, can't do that. That would be really bad. So that's why universal generics says you will be able to use all types, primitives, primitive classes, value classes, whatever, in type arguments, in generic type arguments. So that would give you, let's say, a list of long or a list of rational number. And then the second part is specialized generics. And that's, I think, I'm assuming that like 4 of those 6 PhD theses are probably hiding in that project, in that part of the project. Because what that means is we not only get to write array list of int, because if it's still backed by an object array that's not great, we would still avoid it. We'd still be like, but maybe I do need the performance, I don't know. So let's not do the thing that I actually want to do. Let's not write the code I want to write. Let's prefer performance. I think we're not very good at making that decision, but we do make it every day. And so what specialized generics then says, okay, let's fix that. Let's make sure that if you use primitives, then all the operations that the JVM does on those fields or on those method arguments are actually using the primitive JVM commands and will actually have the same performance as if you would just write an int array for that list. So if all of that happens, all of that is done, we get a bunch of things. So first off, as I mentioned earlier, we have this trade-off occasionally between design and performance, and that, I wouldn't say it goes away, it never goes away entirely, but like a lot of that will disappear, right? Like a lot of that, like I need to have 2 arrays of x and y coordinates because I need to be fast. No, now we can just have one array of point, and then point has an x and y, and it will factually be an array of x, y coordinates alternating, but you can treat it as an array of point, and you write your code as that, like that. That would be much better code, much more readable, and have the same performance. You don't have to, we didn't do that a whole lot, but there doesn't have to be a manual specialization, which is a huge recurring problem, which like toInt function and double stream and float stream, all of those exist because the performance is important, but it means somebody has to sit down and manually write all of that code, which isn't great. You can express the design more clearly, and we get more robust APIs. Ideally, the last point is a little bit of a guess on my end. I think most APIs would be more robust, and most subsystems would be better separated if they communicate with one another with immutable objects. Instead of passing something around that different subsystems and mutate, and then you get crazy results or unexpected results, unexpected side effects. Ideally, we communicate from one subsystem to another with value types, with primitive types that just carry the information but can't be changed. But that's more like my personal hope here. So overall, Java becomes more expressive and more performant. When does it do that? It's not easy to say. So this is like a big project. I hope that we'll see value classes preview next year, and then also primitive classes, maybe. And then if we get primitive classes, I'm very sure that we also get the primitives as classes preview. So that is, let's have the primitive class thing in the language, and this is, let's treat Java's built-in primitives like these. And I think those will come together. I'm just guessing that. And universal generics probably pretty soon too, because otherwise it's really hard to use all of them. Like if they fall apart immediately as you touch generics, that wouldn't be great. But I think specialized generics we have to wait for that a little longer. And like it all really only comes together once that is done. So we're still talking about a couple of years down the road. More deep dives. The State of Valhalla, the first 2 documents in particular, I can highly recommend those. They're really well written, good reads. And the third one is on the JVM model. I'm sure it's also written really well, but it requires much more technical knowledge that I didn't have. So like I failed on that. But the first 2 are really great. Okay, let's take a breath. Let's talk a little bit about other stuff that's happening, because it's not just these 4 large projects that are being worked on, of course. We can't go through all of this, but I just want to pick out on each slide one thing that I really like. So for example, there are lots of APIs were added or changed, and one that I find really cool is Unix domain sockets. So for example, if you have 2 processes working on the same machine, they need to communicate, and it's common to open a loopback and then use HTTP connections for that, which is not as fast as a Unix domain socket, and it's also more of a security hazard because it technically allows other machines to connect to it, which Unix domain sockets don't. They work on the file system. And counterintuitively, Windows now also supports them, which is why they were introduced into Java. So if you have code where several machines on the same, several apps on the same machine need to communicate, you should look into that. It's going to make your app faster and safer. And like it's minimal code change. Then a bunch of usability changes. We have a simple web server now, which is actually what is running over here right now. So this is a presentation that comes as a website. So it runs in Chrome right now. And it runs with the simple web server, which is a new JVM binary, new JDK binary, where you just type jwebserver, and it starts the server in that directory and hosts the local files. Like it's just meant for demo purposes or for experimentation, but it's really neat that this like simple stuff now actually finally arrives in Java, and we can do simple experiments with that. There's continuous improvements in the area of performance and security. If you're interested in startup time, you should look into class data sharing archives, which allow your app to be a little bit quicker on launching. Nothing, it's not going to make a huge difference, but like 10 to 20% is a common improvement. Garbage collectors are improved all the time, and also like all the small and large improvements within the JDK. I think string.format got a whole lot faster, like by an order of magnitude recently. And all these small performance work adds up over time. So if you have in JDK 8 or 11, if you go to 18 at the moment, you really see an improvement there. And of course, security is constantly being worked on. Sean Mullen, who's in charge of that at Oracle, has a great blog which publishes one post every 6 months, which is called JDKN Security Improvements, I think. And like he goes over all the details. One thing that I want to point out is if you're worried that you might deserialize stuff that you actually don't want to deserialize, there's a filter for that since JDK 17, which okay. So there's a general deserialization filter that was in JDK 9. And then this improves on that API, which allows you to say, look, I only want to deserialize stuff that has these and that properties. And if it's not that, it gets discarded very, very soon and quickly. So not only will you not deserialize it, you will also be more safe from denial of service attacks because you will be quicker to discard it. But also Java is not just getting better, it's also getting a little bit slimmer. There's a bunch of weight we gained over time. Not just Corona, but just like in general. And so a bunch of old things are slowly leaving the JVM or the JDK. At the bottom, we see that concurrent mark sweep, Nashorn, and RMI activation are already gone. So if you're on 11, all that's gone if you move to 17. And then there's a bunch of things that are deprecated for removal. Some of them will take a while. So I guess that biased locking and applet API is probably not going to stick around for too much longer. But security manager and finalization, I think, will still take quite some time before they're finally out. But you should be aware of these changes so that you can make sure to make migrations easy. And just some general tips on that without going into any level of detail. If you do want to benefit from these frequent improvements in the JDK, you want to update frequently. There are a couple of best practices that you can stick to. So first of all, stick to supported APIs. Don't just, if you're not sure about the behavior of an API, don't just try it out and then say, oh, well, that's what it does. so I'm just going to rely on that. Now look up the documentation. Maybe it doesn't promise that. Maybe that's an implementation detail, right? Only the Laravel behavior in the JDK, but also in your dependencies that is actually supported and promised and not just an arbitrary implementation detail. Stick to that standardized behavior, stick to well-maintained projects if possible. Like if you have the choice between web frameworks, it probably doesn't make sense to pick the one that was developed by like one dude in 2008 just because it's fancy. Stick to the stuff that's well supported if that's possible, if you have the choice, because those projects, like the large projects, they update very frequently. You have much easier time updating your projects. Keep dependencies and tools up to date. In general, probably a good tip, but much easier said than done, but definitely worth the effort. Also with security-wise, right? But also in this context. Then the second to last one, stay ahead of removals. That's one I really want to ask you. Like, if you don't do anything else on this slide, do this one, please. No, you cannot. No, you have to do a lot of those things on the slide. The first two are important as well. But anyway, so this one is good. A JDepper scan is a binary in the JDK that you can run against jars, or just bytecode in general, and it will tell you which APIs are being used that are deprecated or deprecated for removal. You can use that in your build process, for example, to fail when somebody adds a dependency on a deprecated API within the JDK. So, and then you can also scan your dependencies, right? Because it operates on bytecode. You can technically have, in each build, just quickly figure out, are there any things we're using that could be disappearing? Just to know ahead of time, right? You don't want to be on JDK 8 now and pile on code onto, I don't know, some feature that's already removed or is in the process of being removed. You could already know that, but you'll find out like in a year when you finally do the update. That would be sad. And build on each release, including early access builds. Do that. And it's like you don't have to do that in every build, right? That may be a nightly build that runs on 19 early access. If you have a performance benchmark, that will also be amazing to run that and report back. The build failed. There's some strange performance degradation. Just like report those things back to the email list. This is really your way, or the best way to contribute back to the JDK development as a whole. To come back with feedback, like actual, not just like me, just writing, smart-ass emails, like, no, Brian, I think this feature should look like that. I never used it, though. So like, no, we tried this in practice, and that was what was the result. This is great feedback in general, and it's really highly appreciated. So I want to ask by a quick show of hands. Okay, I can't show you that, because I have to wait for the results. So with a show of hands, I want to find out what's the most recent Java version you're currently running in production. Right, so probably maybe you have several projects, pick the highest number. So who of that would be on JDK 7 or earlier? There's always one person. I'm sorry. Oh man, there's 3. Wow, okay, yeah, banking, huh? So who's on 8? That's hard to guess. It's probably lower than 10% though. Wow, that's good. I'm not going to ask for 9 and 10 because you shouldn't. Who's on 11? That's a lot. So I want to say that's at least half. Okay, so once again, skipping all the shorter releases, who's on 17? That's, okay, let's say another 20 maybe. And so who's on 18 at the moment? Come on. No, please. Wave. No? Ah, damn it. Okay, so of those who are currently on 11, who thinks they'll still be on 11 in half a year? So who is not planning to go to 17? That's, I would say, at most half of the JDK 11 users, which I consider a great result. That means that many, many people, like at least half of the people in this room, will be on JDK 17. Well, hopefully. But probably on 17 by the end of the year, which is a great result, which is like basically what I'm saying here. Java 11 is slowly but resolutely overtaking Java 8. You've already completed that process, but you're also ahead of the curve, right? If you come into conferences, you're probably not representative of the overall crowd. Adoption of 17 from 11 looks good. And always using the latest is uncommon but persistent. Okay, so I'm not sure. Maybe that's just like wishful thinking. Okay, we have 7 minutes left to go through Loom. Let's get enough Loom in as we can. Loom deals with JVM features and APIs for supporting easy-to-use, high-throughput, lightweight concurrency and new programming models. We're not going to get to the programming models. Let's focus on the first aspect of that. Let's talk about a run-of-the-mill request that comes into your web app. You're going to have to somehow interpret the request, parse some JSON, get some information put together. Then you, let's say, query a database. You wait for that, it blocks. And then you process the data that it gives you back, put it into the response, and send its way. And generally speaking, step 1 and 3, they're good resource utilization, right? So you're busy shuffling stuff from memory into CPU, and you're doing some operations, that's good. But step 2 is really poor. You're just sitting there waiting. So how would you implement that request? Two approaches. The one is the synchronous approach, which aligns the level of, the unit of concurrency in your app, namely concurrent requests, with the unit of concurrency within the JDK, which would be threads. And so you just use one thread for each request. That code is simple to write and debug and profile. All the tools understand that. That's pretty easy to deal with. It just blocks on certain calls, which is not ideal. And the number of platform threads, by that I mean like the number of actual threads that, that the regular Java threads are all platform threads at the moment. They're based on operating system threads. They are not for free. They have some costs, so you're using that expensive resource not very efficiently, and that can end up in low throughput when the number of platform threads actually becomes a limited resource. That's why asynchronous APIs started to occur. And the idea here is pretty, not very extreme. You know what, let's use the expensive resource only when the time we actually need it, and let's not just sitting it waiting there all the other time. So use non-blocking APIs with futures or with reactive streams. That stuff is harder to write, and it's more challenging to debug and profile because the tools do not understand all of that well. It's incompatible with synchronous code. So if you have an API that doesn't know about this and it blocks the thread, that's not great. But it does share platform threads. That's why you want to do this, because the expensive resource is much better utilized, and you can ideally end up with much higher throughput. But the problem is you now have a conflict between simplicity and throughput. And once again, virtual threads try to deal with that specific conflict and give you a solution to that. So a virtual thread is a regular thread. And so that word thread there is in code font. It means it's an instance of the class thread. But it has much lower memory footprint. So a thread has in the order of like 1 or 2 megabytes. This would be bytes or at most kilobytes. Has a small switching cost. It's not the operating system who's in charge of it, but the JVM, which has much more freedom to schedule this because it has much less requirements for safety and everything like the operating system does. And requires no OS thread when waiting, basically. So while you're waiting for something, it's basically free. And as I said, the runtime manages virtual threads. How does it do that? This is an implementation detail. Technically, you don't need to know this, but I find this very interesting, so I'm going to tell you anyway. The idea is that there's a pool of so-called carrier threads in the background, which sits there and waits for actual tasks to do. And when you have a virtual thread that does a blocking operation, what instead it will do, it will not block, but it will say, okay, I'm yielding the carrier thread that was executing the actual operations. It can go do something else, and I will continue when the call returns. So if you go over that hypothetical request, what we do in a virtual thread is that the runtime submits, when the request comes in, a task to the carrier thread pool. And then it does its thing, interprets the request, and as soon as it blocks in stack 2, the virtual thread yields. The runtime sees that, takes the carrier thread, puts it back to the pool, and then some other virtual thread can do something. The virtual thread and the carrier thread don't really know about one another. If you are running your code in a virtual thread, you cannot tell that there was a carrier thread running you. Inside that virtual thread, it looks like you're blocking. You're in step 2. You're waiting for something to happen. And when that thing happened, and it unblocks, the runtime takes the virtual thread and the task, resubmits it, and eventually a carrier thread will continue computing it. Which is, it's basically a little bit like all of this async stuff, right? But like under the hood. Like it's not the same, but it has similarities. So I bet a joke that that virtual threads can wait at infinite throughput, essentially. So if you would write this code where you go from 0 to 1 million and create one thread, so you would create 1 million threads that each sleep a second, that's probably a good way to crash your machine. With virtual threads, it's no problem. But this takes a second plus a very tiny amount of overhead to just like start all those virtual threads. They all fall asleep immediately, and the carrier thread just goes through, picks the next of the million threads, puts them to sleep, the next. It's super fast. Also pointless, but nice to see. The more realistic example is that you will use what's called a new virtual thread per task executor, which is a executor, a thread pool that doesn't pool. It just creates new virtual threads every time. And with that, you can then write a code that just like doesn't care that, oh, there's only a limited number of threads, and what do I do? No, you just create a new one every time. You submit your task, you wait for them to be done, you get the result out without having to go into any asynchronicity here. I have 1 minute left. I just want to go talk about performance quickly. Virtual threads aren't faster threads. Each individual task takes the same amount of time it would take before that, probably. You're just going to do more of those at the same time. if you are not CPU bound. If your machine spends a lot of time waiting, Loom is, like virtual threads, other things that are going to enable you to just wait on more things at the same time and just get more things done in the same time frame. So you don't reduce latency of a task, you increase throughput of your overall application. Okay, if I would have more time, I would go into use cases and a little bit of structure concurrency, which is a great topic. I'm going to skip all of that, but I'm going to make you curious by showing you the slides quickly. And so, virtual threads make code simpler to write, debug, and profile, but you will still get high throughput. And having so many threads will give you that concept of structure concurrency. And the virtual threads were already merged. It's already done, which is great because time's up. Okay, I'm NipaFX on Twitter and YouTube and everywhere. Also, I'm working for Oracle, as I mentioned. We have two websites, inside.java and dev.java, that I can only invite you to check out, full of interesting information about, specifically inside Java, about stuff like this while it's happening. We have a YouTube channel where I occasionally do videos. And remember, we're on GitHub, right? Well, OpenJDK is on GitHub. Just go to github.com/openjdk. Look at all the code yourself if you're interested. Thank you very much for your attention.